This video is to support a course that I'm teaching in introductory proofwriting. And here we're going to look at the notion of composition of functions. So let's look at the definition. We want to suppose that we have two functions f and g, and f goes from a to b. So the domain of f is a and the codomain is b. And then g goes from b to c. So let's notice that the codomain of f is the same thing as the domain of g. And that means that we can apply these two functions one after the other. So if we start with a, then we can apply f and land at b, and then we can apply g and land at c. But then if we were to kind of forget that b was there altogether, then we would have one function from a to c. And that function is known as the composition of f and g. In other words, f composed with g. That's how you would say that. And we define that new function as follows. So we'll say f composed with g evaluated at a is equal to f evaluated at g of a. And that's going to be true for all a in a. Okay, so now let's look at some examples. So for our first example, we'll take all of the sets to be the integers. So we've got a function f from z to z and g from z to z. And we're defining f by f of n equals 3n plus 2, and then g of n is n squared. So here, I want to calculate the composition in both orders just to show that it's not commutative, although it is associative, but we're not going to prove that here. So let's notice that f composed with g evaluated at n, well, like I said before, that's going to be f of g of n, like this. And so that's going to be f of n squared, given the fact that g of n is n squared. But now, applying f to n squared, we get 3n squared plus 2. Now let's compare that with g composed with f evaluated at n. So that's going to be g evaluated at f of n, which is going to be g evaluated at 3n plus 2, given that that's how f is defined. But that's going to give us 3n plus 2 quantity squared. But now we could multiply this out if we wanted to. We would get 9n squared plus 12n plus 4. But now clearly this 3n squared plus 2 and this 9n squared plus 12n plus 4 are not equal for all values of n. So here we've got that the composition of functions is not commutative. Okay, let's look at another example. Okay, for this example, we're looking at functions defined as subsets of a Cartesian product. So here we've got f from the set a, b, c to 0, 1, and g from the set 0, 1 to 1, 2, 3. And then if you recall a couple of videos ago, we looked at the precise definition of a function as a subset of a cross b or b cross c, kind of depending on what our setup is. Like for example, up here we would have f as a subset of a cross b, and here we would have g as a subset of b cross c, and those are satisfying some rules. That's what we've got going on here. We've got f is a subset of a cross b, and it's defined by the ordered pairs a0, b0, c1, and then g is a subset of b cross c, in this case 0, 1 cross 1, 2, 3, and it's defined by the two ordered pairs 0, 2, and 1, 3. And now we can look at the composition of f with g, and that'll be equal to the following ordered pairs. So we know the first entry must come from our set a, b, c. So let's see, a, well, it's paired with 0 in f, and then 0 is paired with 2 in g. So that means in the composition, it's paired with 2. And then similarly, b will also be paired with 2, for the same sort of reason. And then finally, we could see that c, well, it's paired with 1 via f, and then 1 is paired with 3 via g. So we have, in the end, c is paired with 3. So that's our composition of f with g as a subset of a, b, c cross 1, 2, 3. just like in this definition, we have F composed with G is a subset of A cross C in general. So now we're going to jump in and prove a couple of pretty standard results involving compositions of functions. And the first such result says that if you compose injective functions, you get an injective function. So that's what we've got here. We've got a function F and a function G. Both are injective, and we want to prove that F composed with G is injective. And we're going to do that using the standard outline for an injectivity proof. So maybe let's go ahead and suppose that we have X and Y in A such that F composed with G evaluated at X equals F composed with G evaluated at Y. And let's recall, in order to finish this injectivity proof, we want to show that this implies that X equals Y. So that's what we're trying to end at. So let's see how we can do that. Well, now applying the definition of composition to both sides of this equation, we'll see that we have F of G of X equals F of G of Y. And now we can work from the inside to the outside. So we know F is injective, in other words, 1-to-1, but that's going to imply that G of X equals G of Y. If the output is the same, then the inputs have to be the same. And then furthermore, since G is injective, we can see that that implies that X equals Y. But now putting this all together, starting here and ending here, we have proven that F composed with G is injective, which is exactly what we wanted to show. So now let's prove a companion result having to do with the surjectivity of F and G. So here we'll suppose that F and G are surjective functions and then show that F composed with G is surjective. So let's see how we can do that. So let's start by taking an arbitrary element from the target space of F composed with G, which will be C. So let's take, we'll call it little c in our set capital C. And then let's recall what we need. So we want to find some little a and capital A such that F composed with G evaluated at little a equals little c. So that's what it takes to show that this is surjective. Okay, so let's see how we can do that. So we'll work backwards, first by finding a little b in B such that G of little b is equal to C. And so this is possible because G is itself surjective. That's what we've assumed. But now we can do that one step further back with F. So now let's take A in A such that F of A equals G of B. And we can do that because F is surjective. Okay, but now we're pretty much good to go. Now let's evaluate F composed with G at A. And notice that gives us F evaluated at G of A, but that's F evaluated at B, but that's equal to C. So looking at what we have taken an arbitrary element of the codomain, and then we've constructed an element of the domain that gets mapped onto that element of the codomain by our composition. So that means that F composed with G is surjective, which is exactly what we wanted to show. And that's a good place to stop.